You know, every single aircraft, from a tiny Cessna all the way up to a giant A380, has this, well, it's kind of like a secret. It's a network of tubes and gauges, almost completely invisible, called the Pitot Static system. And all it does is tell the pilot three simple but absolutely vital things: their speed, their altitude, and if they're climbing or going down. Sounds simple, right? But what happens when that system starts to lie?
Yeah, this is a pilot's absolute nightmare. Imagine you're flying blind through the clouds, relying completely on your instruments, and you just get that sinking feeling that the information they're feeding you is dangerously wrong. And this isn't just some minor glitch. We're talking about the kind of deep confusion that can lead to total catastrophe.
Just try to put yourself in that cockpit for a second. Every instinct you have, every single move you make, seems to have the exact opposite effect on your gauges. You pitch the nose up to climb, but your airspeed indicator says you're slowing down, maybe even heading for a stall. It is a terrifying puzzle. And to solve it, we first have to understand the very air the plane is flying through.
So, okay, how does this system even work? Well, it's all about sensing two different kinds of air pressure. And believe me, understanding the difference between these two is the key to figuring out how these instruments can be so cleverly tricked.
Okay, first up we have static pressure. The easiest way to think about it is just as the weight of the air. It's that quiet ambient pressure that's just there at any given altitude. So as you climb, there's less atmosphere pushing down on you, and that static pressure goes down. And then you've got dynamic pressure. This is the pressure of pure motion, the force of the air hitting the aircraft as it slices forward.
And you know what? There's a perfect way to feel this for yourself. That feeling of the wind pushing against your palm when you stick your hand out of a moving car window, that is dynamic pressure. The faster the car goes, the harder that wind pushes. The Pitot Static system is basically designed to measure both that push and the still air around it to figure out exactly what the plane is doing.
All right, so the aircraft is sensing these invisible pressures. But how does it turn all that into information a pilot can actually use? It does it through three incredibly clever mechanical instruments that have been the backbone of aviation for decades.
First up, we have the airspeed indicator. Now this is the special one, because it's the only one of the three that needs both pressures to do its job. It takes in the total pressure from a tube that faces directly forward, that's called the pitot tube, and it compares that to the quiet, ambient, static pressure it gets from little vents on the side of the plane.
And here's the simple genius of it all. That pitot tube sticking out front, it's capturing the total pressure. So that's the static pressure plus the dynamic pressure from blasting forward. The instrument then just subtracts the static pressure it's getting from those side vents. So what's left over? Only the dynamic pressure, which gives you your airspeed. It's just a beautifully simple bit of math.
Next is the altimeter. Really, this is just a very, very sensitive barometer. It only cares about static pressure. Inside, there's a sealed little capsule, like a tiny accordion. As the aircraft climbs, the outside static pressure drops, which allows that little capsule to expand, and that expansion is what moves the needles on the gauge to show a higher altitude. It's simple and incredibly effective.
And the last piece of the puzzle is the vertical speed indicator, or VSI. This instrument also uses static pressure, but what it's really measuring is the rate of change. It has this really clever trick inside, a calibrated leak. Basically, it's comparing the current outside pressure to the pressure from just a moment ago. That difference is what tells the pilot exactly how fast they're climbing or descending. Okay, so now we know how it's all supposed to work. Let's get back to that really scary scenario from the beginning. What happens when these delicate little openings get blocked by, say, ice or dirt?
This is where a pilot has to become a detective, and fast. Let's look at the clues. So first scenario. The pitot tube gets clogged, but its little drain hole is open. This one's simple. The airspeed just drops to 0. Everything else works fine. Now for the really dangerous one. The pitot tube and its drain hole are both blocked solid. Air is now trapped inside the system. As the plane climbs, the outside static pressure drops, which creates a bigger pressure difference inside the instrument. And the result? The airspeed indicator incorrectly shows an increase in speed. The pilot thinks they're going faster and faster when they might actually be slowing way down. And finally, what if the static port gets blocked? Well, now the altimeter and VSI freeze solid, stuck at whatever altitude the blockage happened. And the airspeed indicator? Yeah, it starts lying too.
But here's the good news. These failures, as scary as they are, leave clues. They're identifiable, and what's even better, they're often preventable.
pilots have tools to fight back, both in the air and on the ground.
So, in the air, a pilot has two main lifelines. The first is pitot heat. It's just an electric heater that melts ice right off the tube. The trick is, you have to turn it on before you need it. The second is the alternate static source. This is a backup valve that lets the system read air pressure from inside the cockpit if the outside vents get clogged up. Now, it's not perfectly accurate, but trust me, it's a whole lot better than flying with frozen instruments.
But honestly, the most important safety feature isn't some fancy button in the cockpit. It's the pilot's own eyes, right there on the ground. That pre-flight check is absolutely non-negotiable. You take off the covers, you look inside for any blockages, and you make sure that tiny drain hole is clear. It's a simple 2-minute routine that stops a major problem before it can ever even start.
And hey, it's not just about ice. When a plane sits on the ground, those little openings look like the perfect, cozy home for insects. A quick check can prevent an emergency caused by a surprisingly common threat, a wasp that decided to build a nest in there.
So after hearing about all the ways it can fail, you might be thinking, this system sounds kind of fragile, right? But the truth, well, it's actually the complete opposite. Its simplicity is what makes it so brilliant.
This elegant system, built on pure physics, has been a reliable core of aviation for over a century. And in the modern world, safety is all about redundancy. Big jets don't just have one of these systems, they have at least two and often three completely independent ones. A single little blockage can't take down the whole flight deck.
And this all brings us to a bigger question, really. In our age of dazzling glass cockpits and powerful automation, this simple mechanical system is still absolutely vital. It makes you wonder, when the screens are showing you something that just feels wrong, how much do you trust the technology versus the fundamental skill of simply being able to read the air?